So today we're going to talk about a special kind of line integral. Having dealt with general line integrals in the last lecture, we're going to talk about a special kind of line integrals over vector fields that are formed by taking the gradient of another function. So suppose we're concerned with a function that is a vector function that is the gradient of some scalar field f. We can consider taking line integrals of this vector field obtained by integrating over a curve the vector field grad f dot t ds. This is also written the line integral of grad f dot dr. And we remember that dot dr is just another way of writing dot r prime of t dt. That comes from the unit tangent and the ds component. The unit tangent would be r prime of t divided by its own magnitude, and ds is the magnitude of r prime of t dt, and the magnitudes cancel and we're left just with this expression here. But now let's go a step further. Let's write out what that would be in the specific case where we're integrating a vector field which is the gradient of a scalar field. So in that case, the three components of grad f would be df dx, df dy, and df dz, and the three components of r prime of t would be dx dt, dy dt, dz dt. And so when we took the dot product, we would get this scalar sum, df dx, dx dt, df dy, dy dt, plus df dz, dz dt. Well, that's nothing more than the chain rule derivative with respect to t of the function f. Okay, so we saw back in the chapter on partial derivatives, that's just our chain rule. F depends on x, y, and z, each of which depends on t. And we get these chains of derivatives, which give us exactly this thing. So this is nothing more than the exact time derivative of the function f, which depends on the intermediate variables x, y, and z, which depend on the underlying parameter t describing the curve c along which we're doing the integral. So because we're now doing an integral of a time derivative dt, we can employ the fundamental theorem of calculus. This is just some scalar function f, and because we have parameterized it on a curve c, on that curve, it's just a function of the parameter t. So we're taking the derivative of a scalar function and we're integrating it with respect to that same variable, which means we can apply the fundamental theorem. So we plug in t equals b, f of r of b, and we plug in t equals a, f of r of a. This is just the value of f at the end point minus the value of f at the starting point. So to review, if we're doing a line integral of a gradient, then we simply get to evaluate the underlying function f from which the gradient was taken at the two endpoints and subtract them. So this is, as our book says, sometimes called the fundamental theorem for line integrals because it is exactly the same structure as the fundamental theorem of calculus from Calculus 2. So the fundamental theorem for calculus said that if we are integrating the derivative of a function of x dx, we just evaluate the function itself at the end point and the starting point and subtract them. This so-called fundamental theorem for line integrals is almost exactly the same structure. If we're integrating along a curve between parameter values a and b of a gradient dot dr, we simply plug in f of r of the endpoint minus f of the initial point, and that gives us our answer. So this is nice for all the reason that Calculus 2 was nice. If we can find this function f, or if we know this function f, which is used to obtain a vector field v, then we no longer have to parameterize the curve along which we're integrating. We don't have to calculate other things related to that parameterization. This r prime of t is t hat ds. And in fact, if we know f, we don't even have to do any kind of integrals whatsoever. In this sense, f is like an antiderivative of v. It's almost like an anti-gradient, you could call it maybe. And if you have that antiderivative, then you don't have to do the integrals, which is exactly what we saw in Calculus 2. So this is a particularly nice property of these kinds of integrals, which leads to some vocabulary. So if a vector field can be written as the gradient of some other function, v equals grad f, then these two things each have special words associated with them. F is called the scalar potential of the vector field v because it generates v when you take a gradient. And the vector field v has the property that it's called conservative. So let's learn a little bit more about the properties of these vector fields. They have some interesting properties, and we're going to list a couple of them. So first, and this is a little surprising at first, but it makes perfect sense once you think about it a little bit, is that if we do a line integral around a closed loop, like you see here, we always get 0. Why is that? Well, it's because integrals of this form are evaluated by plugging in the beginning and the ending points of the line, the curve. For a closed contour, the beginning point equals the end point. This is r initial equals r final. So this is r final, this is r initial, and they're the same point. And so f evaluated at that point is going to be the same in both cases, and we get 0. So when the beginning and initial points are the same for a conservative vector field, the value of the loop integral is always 0. And that leads to another interesting property, that if you give me a point A and a point B, and you talk about doing a line integral between those points, it doesn't matter what path you take. This is called being independent of path, or path independence. How can we prove this? It's a very simple argument. It says, well, suppose I imagine computing the line integral along this curve C1, and I'll get some value, and I could imagine computing the line integral along C2, and I would get some value. But I could imagine doing the following. I could imagine first walking along C1 and computing my line integral, and then walking backwards along C2. And that would be the integral along C1 minus the integral along C2, because we've changed the direction along C2. But if we do that, now we just have a closed curve, because I have gone along C1 and then back along C2, and that's a closed curve, and we just saw that the integral along closed curves is 0. So it must be the case then that this minus this is 0, and so they're equal to each other. That is, the integral along either path is the same. And this proves that you can go along any path and get the same value of the line integral. So that's nice to know. If you're given 2 points, it doesn't matter what path you can take a simple path if you like, because you'll get the same value as you would for a more complex path. There's a couple of other statements. We're working our way here through some lists of properties of these functions, and I promise there's an example at the end. But so these are interesting properties of conservative vector fields, and there's a statement that will make more sense later. It says that if V is a continuous vector field and has this property that it's independent of path, then the vector field is conservative. Okay, so this is basically the converse of what we just demonstrated. We demonstrated that if a vector field is conservative, then the line integrals are independent of path. It's not inherently true, necessarily true, that the opposite statement is true, but in fact it is. There's a theorem to that effect that's described in the book that we won't repeat here. Okay, let's move on. So we have these nice properties of conservative vector fields, and a natural question to say is, okay, this is great. How do I tell whether or not a vector field is conservative? What makes a good test for the conservativeness of a vector field? And unfortunately, this theorem doesn't provide us with such a test, because the conditions that it states are that the line integrals are independent of path. Well, from an applied perspective, that's the very thing that we want to exploit. We want to avoid doing these integrals, parametrizing the curves. And so it's not any good to test for this property by doing the thing that we want to avoid in the first place. So let's try and find an alternate test for conservativeness. So we start by saying, okay, V is some vector field which has a function as its I component and a different function as its J component, two scalar functions P and Q. And let's keep this in 2 dimensions at first. If V is conservative, then it is the gradient of some vector field, all right? In that case, V, which is Pi plus Qj, must be equal to partial f partial x I plus partial f partial y j, right? This is a gradient field. And if V is a gradient field, then P and Q must be related to df dx and df dy in exactly this way. That means in particular that here P is df dx and Q must be df dy. If the vector field is continuous and differentiable, then we should be able to change the order of multiple partial derivatives, which suggests the following test. Let's take the y derivative of this first term, d by dy, and let's take the x derivative of this term, and they should be equal. So if we take the y derivative of both sides here, we get dp dy, and that should be equal to dq dx by the equality of the mixed partial derivatives. In particular, if we subtract these two things, we should get that dq dx minus dp dy equals 0. If the vector field is conservative, then it has this property, and if it has this property, then this statement should be true. In 3 dimensions, the same kind of reasoning holds. The algebra just gets a little bit harder. If V is the gradient of a scalar field, then our Pi plus Qj plus Rk must be able to be expressed in the form partial f partial xi, partial f partial yj, partial f partial zk. That implies these relationships, that P, Q, and R are each equal to different partial derivatives of f. We can then take derivatives of different functions with respect to different variables and get what should be equal mixed partials. So for instance, if I take the y derivative of P, that should be equal to the x derivative of Q, just like in 2 dimensions, which gives us one statement that Qx minus Py is 0. But we can do the same thing with the other mixed partials. dq dz should be the same as dr dy, and that gives us dr dy minus dq dz equals 0. And similarly, the xz partials give us a third condition, dp dz minus dr dx equals 0. And for a 3-dimensional problem, all 3 of these must be true at the same time. So that's a little bit more complicated. This looks like a great test. We just calculate these partial derivatives, we see if they equal each other, and we're good to go. That's sort of a delicate statement, though, to say that that is in fact true. So if the function is conservative, then definitely these are true. To prove the converse, though, is a little bit delicate. Again, we omit the proof, but we simply state the theorem. If these equations that we just described, if all 3 of these hold at the same time, then line integrals are independent of path, and in the previous theorem we saw that if line integrals are independent of path, then the vector field is conservative. Now there's a small caveat here. This is only true if it holds in what's called a simply connected domain. That is a domain with no holes, because if there's some hole where this isn't true, and we don't know what's going on the inside of some contour, then we're not necessarily guaranteed that line integrals are independent of path, because we don't know what's going on in here. So all this means is that if this stuff is true in some domain that doesn't have a hole in it, then we're good to go. Okay, that is a lot of theory. Let us now do an example. So here's how it all works. This is the part that you should pay the most attention to before coming to class. Here we have some vector field. Compute the line integral over the curve shown, and the suggestion is that this might be conservative. So first, we check and see if it's conservative. This is P, this is Q, and this is R. We need to check and see if these relationships hold. What is Qx? That's Z, minus Py, that's also Z, and so they cancel and it's 0. Good to go. Ry minus Qz turns out to be x minus x, also 0. And Pz minus Rx turns out to be y minus y, also 0. You should take a moment maybe to verify that these are in fact the partial derivatives, because I went through it pretty quickly. So these three equations are true. They hold everywhere. And so the vector field is conservative. That means there exists a scalar potential F. Now we turn to the question of how do we find F? We know that P is df dx, we know that Q is df dy, we know that R is df dz, and we have P, Q, and R. They're given to us in the problem. So we ought to be able to find F itself by integration. So, as indicated here in the text, though, we have to be really careful because we're only given the partial derivatives. We're going to here illustrate the procedure which our book calls partial integration. If you ever wondered if there's an analog of partial derivatives, then I suppose you could say, yes, there is, and here we're going to try it. So let's start with x, fx. The x partial derivative is p, and we're given p. So that tells us that df dx is yz. This is p. So we can integrate both sides with respect to x. On the left we get f, and on the right we get xyz, but where we would normally get a constant of integration, because here we only have a partial derivative of x, we now get a undetermined function of integration that depends on both y and z. And you can see that this should be true because if we now take the x derivative of both sides of this, we get df dx, and because this doesn't depend on x, it should vanish. So this is the most general integration quote-unquote constant that comes when we're given the partial derivative of f with respect to x. So this is the only thing that's different from regular integration. Now we have something for f. We go to the next equation. Partial f partial y is q. We take this expression for f, we take its y derivative, and we put it here. We get xz plus partial a partial y, and that must equal q, which is also xz. So those cancel. The xz's cancel, and we're left with partial a partial y is 0. That implies that a is a constant, but again, a depends on y and z, and we only had the partial derivative of a with respect to y. So that constant isn't a constant. It could in fact be a function of z. You can verify by taking the y derivative of both sides. Partial a partial y equals 0. So this is the right general thing to add after the integration. We're almost done. We need to do one more integral. We take this new expression for a, plug it into f, and then take the z derivative. So fz, which is xy plus db dz, which is now a full derivative, equals r, and r was xy plus 2z. So that gives us this expression here. Again, we have these two xy's that cancel, so they disappear, and we're left with a simple ordinary equation for b. We integrate both sides, and we get b is z squared, and I could be precise and say plus a real constant. Let's call it d. No, c is fine, where that's actually a constant. So we've now constructed, by these series of partial integrations, the scalar field f of x, y, and z is xyz plus z squared, and you could say, if you wanted, plus a constant. So now that we have f, we can simply do this contour integral along this weird contour, this helical cone contour from 0, 0, 1 to 1, 0, 0. We don't have to parameterize it at all because this is a conservative vector field. We simply plug in the endpoint, 0, 0, 1, minus the initial point, 1, 0, 0. We evaluate that at 0, 0, 1. We get 1, and we evaluate it at 1, 0, 0, and we get 0. I see actually that I've done this backwards. The way the contour was organized, this was the end point, and this was the initial point, and so in fact we should get -1. But because we found the vector field was conservative, and because we constructed the scalar potential f, we didn't have to parameterize the curve. We still had to do integrations to find f, but we no longer had to parameterize the curve because these integrals are independent of the exact shape of the curve.